Thanks for joining me here at Stanford University. I'm with Professor Chelsea Finn, who's with both the computer science and the electrical engineering departments. Chelsea leads a research lab that does cutting-edge work applying machine learning, especially reinforcement learning, to a range of robotics applications. So I'm really glad to have you here, Chelsea.
Happy to be here.
So I know that before you settled into working in computer science and machine learning, you actually considered a lot of career options ranging from biology to aerospace to, computer science and electrical engineering. So what made you make this choice?
Yeah, so I was always drawn to engineering because I really like solving puzzles and solving problems. And when I arrived at MIT for my undergraduate, I was considering different engineering majors. And what really drew me first to computer science was that it gives you a lot of flexibility in terms of the different paths that you can do. Essentially, computer science empowers you to build lots of different things with software, with code. And with that, I could eventually go into biology if I wanted to. I could go into robotics. There's all sorts of really exciting things you can do with computer science. So that landed me in computer science. And then once I decided on that, I really enjoyed a lot of the math that goes behind AI, like probability and statistics. And I was also really drawn to this challenge of how can we build a computer that can see like humans do, that can perceive things in images and can take actions in the world.
Yeah. So it was almost as if your choice was, if you do computer science, you could do, anything. And so that makes it, I guess, what Mark Andreessen said, software is eating the world. And I think Jensen Huang said AI is eating software. And it feels like when you work in machine learning, you get to poke your nose in all corners of the world and do fun things. And
Absolutely. I think machine learning is a really exciting place to be. And I mentioned that computer science is very flexible and opens lots of doors, and I think that machine learning is very similar to that. There's so many different things you can do with machine learning and so many different applications. I'm really excited about applications in robotics, but we've seen lots of different applications in language processing, in biology, and in other fields.
Yeah. So your specialization, of the many things you do, a large fraction of your work is in robotics. And when, people look at the popular media or social media, you see these videos of, for example, humanoid robots jumping up and down and doing parkour and doing incredible things. How should one think about what robots really can and cannot do today? Because there are these amazing demo videos that looks like can do almost anything, but how should one decide what is actually doable?
Yeah. The videos that we see online from Boston Dynamics, for example, of robots doing backflips or doing parkour in a course are really impressive because they look really complicated, and it's really easy to, in some ways, anthropomorphize the robot and think that if you saw a person doing that, that would be very impressive, and they would probably be able to do lots of other really impressive things. And the catch is that in robotics, in those videos and in many impressive demonstrations of robotics, the robot was set up for that particular environment, and it was tuned to do well with that setup. And if you change something about the environment, about the setup, about what it's supposed to do, then the demo no longer works. The robot will fall flat. So the big challenge with robotics is getting robots to generalize, to be able to handle lots of different scenarios with lots of different objects, with lots of different environments. And right now, robots can do things in very controlled environments, like in factories, and they're very useful in factories. And what I'm really excited about and what's really hard in robotics is giving them the flexibility and generality of the skills that humans can do.
Hey, just to dig a little bit more into the specific one-off, one environment thing before going to generality, when someone sees the next cool robotics demo, how should they think about it, or what are the questions they should ask themselves?
Yeah, so I think that the first question that someone can ask is, what will happen if something changes in the environment? What will happen if you move a block, or if you put the robot in a slightly different position when it starts? Oftentimes you don't see those kinds of tests of the system's robustness or resilience to those variations. And if you do start seeing those demos where actually you kind of poke the robot or you change the environment a little bit and it still works, that's when I think we can be really impressed.
Cool. So a lot of your work has specifically been on making robots robust, to generalize or apply to lots of different environments. Just tell me more about that work and how you approach this problem.
Definitely. So in other areas of machine learning, we've seen huge successes where we take a very large data set, like you take all of Wikipedia and you train a neural network to be able to model the data in that very large and broad data set. And in robotics, one thing that I'm excited about is if we can somewhat replicate that sort of success, if we can collect a similarly diverse data set and allow robots to learn from that data set. Now, this is challenging for a couple of reasons. One is that we don't already have an existing data set. We don't have Wikipedia for robot motor control. There isn't data lying on the internet of how exactly to move a robot's fingers to tie shoes, for example. So we don't have tons of diverse data already. But fortunately, robots in principle should be able to collect data themselves. And that is an opportunity because it means that we might be able to collect a large amount of diverse data by allowing the robots to collect their own data. But it's also a challenge because it means that we need to figure out how to allow robots to collect data that's useful and diverse. And so there's lots of different things that we explore in terms of approaching this problem. Some is allowing robots to collect their own data in lots of different environments. Some is showing demonstrations to a robot of how to perform a task. We've also explored a little bit of how to use data from the internet, like videos of humans, to show a robot how to do a task, and incorporating all of these different data sources to allow robots to, once they've hopefully seen very diverse data sets like this, they might be able to generalize not just to the one scenario that they saw in a lab environment, but possibly the real world in the long term.
One of the things we've seen is machine learning, reinforcement learning algorithms are great at playing video games because you can get, essentially infinite data playing a video game with yourself. What do you think of the role of simulation?
Yeah, so we've definitely seen lots of successes of AI systems doing very well at video games. And simulation is somewhat similar because we can collect lots of data in simulation as well. One challenge with simulation is that the physics in the simulation engine are not exactly the same as the real world. We know generally the laws of physics, but the friction on a table, for example, may not be exactly known, or the friction between the grooves on a cap and a water bottle, if you try to screw a water bottle, modeling that is very difficult. And it's prone to errors. And then when you try to train a policy in that simulator to close a water bottle, for example, and then deploy it in the real world, it actually doesn't work because of those errors in the simulation. So I think it's a promising data source, but because of these inaccuracies and this challenge of transferring something that was learned in simulation to the real world, I don't think it's the only approach that we should bet on. I think that we should try to leverage lots of real data.
And is it, I wonder if it'd be surprising to someone watching this, why is it so hard to simulate the real world? It's just the water bottles, two pieces of plastic, and somehow we can't seem to figure out what's going on with two pieces of plastic.
Yeah, so I think that there's lots of challenges. I mean, first is just modeling the low-level physics. A lot of simulation engines out there, they will model time at a certain discretization. And in reality, time is much more fluid than operating at like 100 hertz or something like that. And to actually accurately model these things, you may need to actually model at a very fine time discretization, and that gets very expensive. And then your simulator may actually be slower than actually running things in the real world, and then it's no longer useful in comparison to collecting data in the real world. And then the second thing is the real world is super diverse, and so actually creating the content of all of the kind of objects that you encounter, even in everyday life when you're eating lunch or when you're kind of cleaning up a table, creating all of that content is actually a really manual effort. And usually in machine learning systems, you want to kind of do away with the things that require a lot of manual effort and try to automate and automate things so that they can be scaled up.
Yeah. And in fact, in terms of the diversity of environments, today factories work great in robots where the environment is relatively controlled, relatively few, unexpected things happening on average. I know some of your work has been looking to send robots into people's homes and do things in people's kitchens. That's one of the most uncontrolled environments in the world. Can you say a bit more about that?
Yeah, absolutely. So I think that the controlled environments are the ones where we've seen a lot of success. And in the long term, I would love to see robots that could go into any environment like a home or an office and be useful to people. And to do that, we want to actually start collecting data in those environments. Oftentimes in robotics research, we collect the data once in a lab environment and learn based on that data. But if we only collect real data in a lab, we're never going to actually get the robots out into the real world. So we're trying to start data collection efforts, actually putting robots into the real world so that they see the diversity of all these different homes, rather than kind of the narrow data that you see in a lab.
So I want to get your gut about one thing, which is you talked about wanting to get a robot to go into a brand new home and make a bowl of cereal. Right, challenging tasks, liquids, cereal, fridge. What's your gut about how many different homes, how many different kitchens a robot will need to see? So how many training examples do you think a robot will need in order to have, a good chance of doing on the N+1, on the next kitchen?
Yeah, so I think it really depends on how hard the task is. If the task is as simple as, maybe pressing a button on the microwave, then I think that you may not need quite as much data for that. But I think even for a new kitchen, you probably need still quite a large number of kitchens in order to generalize to a new one, maybe 20, maybe 100. If it's a task that's more complex, like making a bowl of cereal, it's something that's super simple to people, but it's actually really hard for robots because there's lots of different steps involved. For that, I think you need more data, and probably also more kitchens as well. Maybe in the thousands. And I also think that even if we had thousands of kitchens of data or tens of thousands, my guess is that the problem still wouldn't be solved fully. We've seen applications like autonomous driving where there's tons of data and the problem isn't quite yet solved. So I think we also need to try to go beyond the data distribution and also allow robots to adapt on the fly in a new environment.
Wow, thousands. That's higher than my gut, but that's interesting. Interesting to see how it plays out. Yeah. And so on the theme of making robots more robust, I know a lot of your research work was also on meta-learning, or learning how to learn, rather than us telling a computer, this is a learning algorithm, to how to get a computer to even get better at learning. Can you say a bit about that?
Yeah, absolutely. So part of the motivation is that if a robot encounters a new kitchen, we don't want it to just run what it learned in that new kitchen. It may actually need to adapt and learn on the fly. It may need to, for example, if it's trying to open the door to a pantry and the door is a little bit different, it may need to take a little bit of experience and trial and error on that door in order to figure out how to open it. And we want to allow systems to do this sort of learning process on the fly at test time in new scenarios. And unfortunately, if you just run machine learning from scratch at test time on a very small amount of data, that won't work very well. You need large amounts of data in order to learn something. So what meta-learning tries to do is it tries to take experience in previous kitchens or previous tasks and optimize for the ability to learn new things, the ability to learn new things based on having learned lots of previous things.
Yeah. So for example, what's the best learning rate with which to adapt to new kitchen setting and lots of other things one could tune?
Yeah, absolutely. So the simplest setting is if you're only optimizing for one parameter, like the learning rate, in a new situation. And in more complex meta-learning algorithms, you can sort of optimize for the entire learning algorithm.
So I think of you as one of the world experts in meta-learning. In fact, if I remember, this is a big part of your PhD thesis, which you did way back with Peter Beal, who was my PhD student at Stanford. But so just say more about how meta-learning works.
Yeah, so there's a few different approaches to meta-learning, but the approach that was in my PhD thesis was essentially putting a learning problem inside another learning problem. So it's actually forms this bi-level optimization, this two-level learning problem, where you are actually trying to optimize for all of the parameters in this inner learning problem, such that you could achieve faster learning or more efficient learning.
Yep, I remember reading some of your early papers and very impressive. So lots of software algorithms, machine learning algorithms, reinforcement learning algorithms. one part of your work is you also run a robotics lab with robots running around, robot arms. I'm curious, for someone that has not yet spent a lot of time in a robotics lab, can you tell us what it's like if a student were to join your lab? What's it like to show up at work in the morning and work in a robotics lab?
Yeah, so in the lab, it's not all that different from running machine learning experiments where you run code, you try to train a model, and then evaluate that model. But in addition to those everyday things, there's also interfacing with the real robot. So oftentimes a lot of projects might start with a simulation and start iterating on algorithms using a physics engine that might involve actually kind of designing aspects of the simulation to test the hypotheses you want to test. And also sometimes projects won't involve that simulation step, or maybe you've already iterated in simulation, and on the real robot there is everything from setting up the control stack such that you can actually command the robot to move to a certain position, to setting up the cameras, to collecting data with the robot. That data might be, you might be collecting data by using like a VR controller, for example, to tell the robot to move to certain positions. And then also actually, when it comes time to evaluate a model, it involves actually running that on the robot and seeing what the robot does in real life. It's a pretty fun process, at least for me. I think it's very rewarding to actually see the robot do something rather than just see some numbers or some accuracy of your model. But it also requires a little bit of persistence because robots can break down. You might have a motor that breaks. You may not have set up the camera correctly. It might be giving you all zeros, for example. There's many more bugs that can come up than in a system without a robot.
So, number of people have had experience debugging software, and then there's debugging machine learning algorithms, which has different practices and ideas. And then can you say a bit about what debugging hardware in a robotics lab is like?
Definitely. So I think that in general with debugging, you want to rule out possible sources of errors, possible sources of bugs. And oftentimes you might have a guess that it is from the software or the hardware. And from there, I think that many of the machine learning things will apply. You want to look at your data. And because a lot of the data is actually collected in the lab, it may not be from a data set, then there may be something that is wrong about it. And you may want to actually look at the images that the robot is seeing, maybe visualize some of the features that your model has learned. You can also, I guess one thing that we did recently is we wanted to actually deploy a policy on multiple different robots. And so we would actually replay actions on a robot and make sure that the robot was reproducing a certain motion that we wanted it to reproduce. So I guess I don't know if it's really, how you debug depends a lot on the problem. I don't know if there's any one way or any kind of single bug that comes up the most because there's all sorts of sources of bugs. But yeah, that gives us a little bit of a sense for what it looks like.
And I always thought one of the lovely and frustrating things about robotics as opposed to software is in software, if you make a mistake, you can always revert back to an early version of software. But that time that you do something and your robot breaks and then you go, boy, that's another 2 months of work or something to rebuild that. That's a unique experience in hardware.
Definitely. And because we're doing a lot of work on the software side of things, we typically try to get robots that won't break, by very nice high-end robots so that we can worry more about the software and less about the hardware. But if there are cases where a robot might break, we try to get robots where you can pretty easily swap out parts, where if one motor breaks, you could just swap in a new motor rather than having to repurpose the whole thing. But certainly there's lots of challenges that come up.
Yeah. And I used to fly autonomous helicopters. So every time a helicopter crashed, fortunately we managed to keep it safe and away from people. Then there's this frankly destroyed helicopter that we have to just go build a new one. But it's nice when you don't have to do that too often.
Yeah, fortunately arms do not crash too much.
I see. Yeah. Maybe I should have chosen work on that instead. So in your robotics lab, one tool of choice that you've often used is reinforcement learning. can you say a bit about the practical lessons, tips and tricks for how to apply reinforcement learning, amazing algorithms to your hardware robots?
Yeah, so reinforcement learning is a really appealing framework for robotics because in principle, it would allow a robot to learn something completely on its own through trial and error from data that it collected itself. And so it's something that we're really excited about for that reason, but it's also really challenging for a number of reasons. So first, reinforcement learning typically assumes that you're given some reward signal, some feedback. And if you're trying to learn how to play a game, like play a Pong or another Atari game, you can just use the score as the reward function and just try to maximize your score. But the real world doesn't give you a score. It doesn't give the robot a score when it tries to learn something. And instead, the robot might need to learn its own reward function. It might need to learn what it means to accomplish a task at the same time as also trying to learn how to accomplish that task in the physical world. So that's one big challenge and one way that we approach it. Another challenge is typically in this trial and error.
And so how do you learn the reward? Like from a demonstration? How do you learn the reward?
Yeah, so we learn it in a few different ways. We often at least give it some examples of what success looks like. And we also sometimes give it a full demonstration of this is an example of what we want you to do. And then you can get into techniques like inverse reinforcement learning, which you worked on a long time ago as well, and actually try to kind of invert the reinforcement learning process and try to figure out what reward function underlies this behavior. So beyond learning reward functions, another challenge is autonomy in the process of reinforcement learning. So typically you think of it as a trial and error process where you try to solve the task and then you then want to kind of try it again. And in between trying the task and trying it again, you need to somehow get back to some starting point. And maybe, for example, if you're trying to learn how to do a backflip, trying it again will involve standing up after you fall down. But actually, sometimes learning that resetting behavior is also quite challenging. And there's this challenging interplay between learning how to do the task and also learning how to recover from all the ways that you failed at the task in the entire process of doing that.
It's really automating the research process to let you run repeated experiments without having to, lug a robot around every single time to put it back.
Exactly. Yeah.
Cool. Very cool. And in fact, in your application of reinforcement learning, I think you were one of the earliest researchers. You're among the earliest researchers to do, more or less or completely end-to-end robotics, end-to-end reinforcement learning. Can you say a bit about what that was like in the early days and why you went that route?
Yeah. So at the start of my PhD, deep learning was just starting to become popular after AlexNet was showing that you can do very well with deep neural networks trained end-to-end for computer vision. And I had just arrived at Berkeley for my PhD, and there were some people that were working on reinforcement learning with neural networks. And I was pretty excited about that work, and I wanted to see, in the past work, it was all blind. The robot wasn't using cameras in any way. And I wanted to see if we could learn a neural network that directly maps from the images taken by the robot's camera to the torques applied to the robot's joints. And in that first project, it was a lot of work to try to actually get that initial result. But we were excited to see that we actually could get a single neural network that could learn something like screwing a cap on a bottle or putting a coat hanger on a coat rack. With a single neural network mapping directly from pixels to torques. And it was a pretty exciting result. It was definitely very different from what the rest of the robotics community was working on. And I think the paper that we worked on was actually rejected twice because people didn't like deep learning. They didn't like, roboticists didn't like that these neural networks were very black box and you couldn't understand them. But eventually got published and was accepted. Now it's actually become a much more prominent paradigm in robotics where a lot more people are now training neural networks to represent the policy, to represent how the robot chooses actions based on the camera images.
I think that early work you did was quite visionary and set an important new direction for the field. What's your prediction for where this will go? Do you think the percentage of practical robotics work that is trained end-to-end, how much do you think that will continue to go up or not?
Yeah, I certainly think that it will continue to grow quite a bit. Still not all of the robotics research community is looking at these kinds of approaches, in part because there are useful techniques in control theory that are useful, especially in controlled scenarios like we talked about. But I think that it will certainly grow. I think that especially as the machine learning field continues to make really impressive advances, I hope that will convince more people that this sort of paradigm is really promising for robotics as well, especially in terms of handling the vast degree of variety in objects and environments in the world. In terms of looking forward, in terms of like understanding what might happen in the next 10 or 20 years in robotics, one thing that I'm really excited about that we touched on a little bit is trying to train robots on broader data sets. A lot of the field of robot learning is still collecting a data set for a project in a lab and then training on that small data set. It's small because it has to be, because you collected it for that project. And I think if we imagine that if computer vision researchers had to collect ImageNet for every single project that they did, they probably wouldn't be making that much progress. And so I think that my prediction, at least for the coming years, is to move towards a paradigm where we reuse data sets a lot. We use much larger data sets, and ideally are kind of sharing data sets across institutions, across robot platforms, and scaling up the data that these systems are trained on such that they can generalize more broadly.
That's an exciting vision. And how do we get there? For images, everyone uses, PNG files and GIF files and JPEG files. So the data is highly portable and highly shareable. If different research labs just have different pieces of hardware, how do you make that happen for robotics?
Yeah, so it's definitely challenging. The place that we're starting that I'm quite excited about is first trying to actually have a little bit of consensus, bring the community together to say, okay, let's start with this robot platform with roughly this setup, so that we can at least standardize on some of it, and then try to collect lots and lots of diverse data on that fairly standardized platform. Start from there, and then if we're able to get some signs of life and some positive success from collecting a broad data set with those standardized choices, then starting to standardize less and less and move maybe the same robot, but with a different control stack. And then maybe starting to move towards different versions of that robot, different grippers, and ultimately lots of different robots and lots of environments.
Cool. No, right. This is exciting vision. And in fact, so this is one of the things you're doing in robotics. Just looking more broadly, with all the work you're doing in reinforcement learning, some not even applied to robotics, but to other applications, where do you hope reinforcement learning and robotics will go in the next many years? Yeah,
so I think that I'm hoping that it will move towards these reusable data sets and very broad data sets. I also think that even beyond robotics, I think that there's lots of other applications of reinforcement learning as well. So for example, in some of our recent work, we applied reinforcement learning, and actually meta-reinforcement learning, a combination of meta learning and reinforcement learning, to education, to give feedback on student work, where students would program a game like Breakout, and then the system would actually play the game and find the bugs that the students made and give them feedback on how to improve their program and how to continue to learn how to code.
No, that's very cool. In fact, robots are so visual, sometimes it's easy to forget that reinforcement learning is a general technique for decision-making with delay rewards that's useful for many things other than robots too. Yeah. Like, frankly, I when I was doing more robotics work, I used to try to get all my PhD students to learn to solder. I don't know if that was
I learned how to solder in undergrad, although I don't think I actually ever used that in my robotics work.
Oh, wow. I see. Oh, maybe things have moved on, but I had to. Yeah, interesting. Yeah.
I think we would just buy robots that didn't need some soldering.
So your journey has led you to do cutting edge work in reinforcement learning and robotics. I'm curious what advice you would have for someone looking to break into reinforcement learning or to robotics. Not everyone owns a cool robot that can easily program, but how should someone get started?
Yeah, my main advice would just be to try to get your feet wet and just try to build something. Try to program and code something up. There's lots of different things that you can do. And I think that learning by trying to build something, by trying to do something is one of the coolest ways to learn because you have a certain goal in mind.
But would you build something using a simulator robot, or do you think we should just, build a little robot?
I think that starting with a simulated robot is probably the easiest, and there's less of a learning curve and less things that you have to do. You don't have to go out and buy hardware. That said, I think that also trying to work a little bit with hardware right off the bat is great, and it definitely teaches you about how hard robotics is. Robotics is really hard, but also by kind of struggling to get the robot to do something, it makes it all that much more rewarding when it actually does something cool, when it does something that you wanted it to do. And I don't know, some of the robots that we use are fairly expensive, but nowadays there's actually lots of robots that are fairly inexpensive that people can buy, or you can kind of build your own robot by connecting wheels and a camera, or maybe even a smartphone together to build something. I actually got started with Lego robotics in middle school, and you can also build robots out of Legos and get started that way.
Yes. Actually, I remember I went to Lego robotics competitions when I was in middle school or something, and that was an interesting set of experiences. So to someone, taking the machine learning specialization, if their goal is to work in reinforcement learning and robotics, what else would you recommend they look at? What are the other resources you think would be helpful?
Definitely. So there are resources in terms of like just learning about reinforcement learning, and there are kind of courses online. There's also kind of course videos. There's textbooks like Sutton and Bartow, and so those are lots of resources. I also think that there are lots of, videos online, tutorials, code bases. You can actually check out a physics engine like the Majoko physics engine, which is freely available, and try to kind of explore with that. So yeah, those are a few resources. There's also one thing that we use a lot to interface with robots is called the Robot Operating System, or ROS. And so learning about that can also be useful.
That came out of my research lab way back, working with a Willow Garage. Yeah, it's good times. Sorry, didn't mean to interrupt.
Yeah, so I think that those are some of the resources, and not too much more than that.
Cool. Yeah, very cool. It feels like, with the world moving forward and evolving, it feels like the number of paths for someone wanting to get involved in this is even growing, and probably gets a little bit easier every year for someone to enter this field. So this is an exciting time to be in.
Yeah, definitely.
Thanks for joining me here at Stanford University. I'm with Professor Chelsea Finn, who's with both the computer science and the electrical engineering departments and leads a research group that does cutting-edge work on applying reinforcement learning and machine learning to robotics and other applications. Thanks for joining us, Chelsea.
Yeah, happy to be here.